Welcome to 5th International Symposium on Multidisciplinary Studies and Innovative Technologies. Due to COVID-19, we are organizing the symposium virtually. I hope this epidemic will end as soon as possible. Now, Mr. Ahmet Elbir from University of Luxembourg will give their speech. Mr. Ahmet Elbir, take the floor, please, if you are ready.
Okay, thanks. So in this talk, we will talk about machine learning applications in wireless communications.
Who's that?
Let me briefly talk about myself. So I'm a researcher at Düzce University, Turkey, and I'm also a research fellow at the University of Luxembourg and University of Hertfordshire. I'm a senior member of IEEE, and my main study of interest are I'm working on array signal processing, wireless communications, and machine learning. So I will start with the brief motivation of machine learning in wireless communication. Then we will introduce the learning schemes that can be used and useful in wireless communication. We will talk about how to generate the data for learning applications, and we will at the end talk about the advanced learning applications in wireless communication. So we basically use, or we are interested in using machine learning in wireless communication for mainly three reasons. The first one is robustness. So we require robustness, robust performance against the corruptions or imperfections in the data. So these benefits are these are actually for example, for model-based techniques. Instead of using a model-based technique, for example, solving an optimization problem, we are interested to use a machine learning approach so that we can obtain a robust and easy to adapt performance. So the learning models are that can be easily updated for the future incoming data, and they can adapt to the environmental changes. For example, so we can use as much as the training data, so that we can train the learning model which is much more data, and the learning model can be adapted to the environment. And the third advantage is the lower training computation complexity, which can be very useful as compared to the model-based technique. And in deep learning, so deep learning can be used for various physical layer applications in wireless communications. For example, here we have a diagram for wireless communications stage from base station to a mobile station, a user. So we can use a learning model, for example, for signal detection. So in this case, we have the input as the receive symbols, and the output can be the transmitted symbols, which are the clean symbols. It is also possible to use it for channel estimation. To estimate the wireless channel, we have the true channel data during training at the output, and we have the input as, for example, the received pilot signal. It is also possible to use it for antenna selection. Here, we can use a classification layer at the output. Each class can be represented by the best antenna subarray, for example. And we can also use it for beamforming and use the localization technique. In this case, we can use the channel matrix as input to the learning model. So there are some learning schemes that are very useful to implement. For example, the best one, the most useful one, is supervised learning, because in supervised learning we have an input and output structure, and in this case the learning model basically construct a mapping and nonlinear mapping from the input to the output. For example, in this case, we have input data which can be channel matrix, for example, and the output can be beamformer vectors. Beamformer vectors are used in, for example, in massive MIMO systems in 5G networks to steer the beams towards the users. And in unsupervised learning, we don't have an output data. I mean, we don't have a labeled data. So we have a certain number of data which are not labeled. So the main objective of using unsupervised learning is to cluster the data so that we can obtain at the end a cluster of data parts. And in reinforcement learning, we also do not have a label. However, we have a cost function. So we have an aim to optimize the cost by using the input data continuously so that of receiving data from the environment, and we have a reward and punishment mechanism so that the learning model can update and optimize its parameters to optimize or minimize the cost of the problem. So in this case, we can use all of these techniques, supervised, unsupervised, or reinforcement learning for channel estimation. Channel estimation actually can be better used with supervised learning for beamforming or resource allocation problems, beamforming problems, antenna selection problems, and also localization problems. We can also categorize these schemes as centralized, federated, online, and transfer learning. So in centralized learning, we have a center, we have a parameter server, and we have users. The user transmits their data to the server, and the server uses these training data to train a learning model. And after training, the parameter server shares the model parameters to the users. This process has huge communication overhead because the users need to transmit their data sets to the server, which is communicationally prohibitive. Instead of doing this, we can use federated learning architecture. So in federated learning, we have a number of users. Instead of transmitting the training data set, for example, here, instead of transmitting the training data set, we can only transmit the learning model parameters. So each user computes the learning model parameters by themselves and only transmits the model parameters to the base station or the server. And at the server, these parameters are aggregated and sent back to the users. So this process is conducted iteratively, and at the end, we have a trained learning model, and this is much communication efficient way of training a learning model. In online learning, we have a offline data set, which is a big data set, and we train the learning model, and we freeze a few layers of the learner network and update the other parameters by using an online data set, which can be a small data set. So the main reason of using online learning is to adapt the environment so that the learning model parameters can be updated corresponding to the environmental change. Similar to online learning, we also have transfer learning. So in transfer learning, instead of using offline and online data sets, we have two different data sets, such as source and target data sets, which are actually correspond to the two different problems. So, for example, we have a learning model to solve the problem of, for example, image classification of human images. So we want to use to classify the animal images. So we can use the pre-trained learning model and update its parameters slightly, and we can obtain a new model. We have different model types. For example, multi-layer perceptrons, these are actually used in conventional machine learning techniques. not deep learning, in machine learning techniques, we have very small number of, we have very small number of layers between input and output. So deep learning basically based on the using much deeper architectures such as convolutional neural networks or convolutional only neural networks, which do not have fully connected data. We also have generative adversarial networks, which are very useful on generating the training data set. So let us talk about how to generate the training data. So to solve an optimization problem with machine learning or to solve a problem in wireless communication applications, we need to first generate the training data set and train the learning model. So to do this, we first need to collect data. For example, for channel estimation problem, we first need to collect the receive pilot signals. So we have users, each user collects data, and we also need the channel data, the label data to train the learning model. So we first have the receive pilot signals, which can be used as input. And then we also need a model-based algorithm that can be used to obtain the label data. And once we collect a sufficient number of data sets, and we can train the learning model with it. Also for beamforming problem, so in wireless communication, we need to steer the beams in 5G networks to the users. So these beams are actually generated by playing or changing the phase shifter values at the base station. So these phase shifters introduce a certain amount of phases, which can be regarded as beamforming weights. So to obtain these weights, we first need to solve an optimization problem, and we need to obtain the solutions by a model-based approach, and we need to teach them to the learning model so that it can predict the learning model. It can predict the beamforming weight when it is used. So it is also possible to use multiple learning models. For example, in this case, we have a first learning model is used to estimate the target direction. So here we have a joint communication and radar scenario. So we have both radar targets and we have a communication user. So here the car is equipped with a radar communication equipment, and it transmits different multiple beams to both users and radar targets. So to solve this problem with deep learning, we have two learning models which are cascaded. So we first use the array output, which is actually the collected data at the antenna. So we first use it to estimate the radar target direction, and by using this information and the channel information from the communication side, and we can obtain the hybrid beamforming weight at the output of learning model. So now we will talk about the advanced applications of deep learning. As we talk about it, we can use multiple learning models cascaded in a cascaded version to solve a joint problem. So, for example, we have a joint beamforming and antenna selection problem. So we designed two different learning models. Here we have two convolutional neural networks. The first one is used for antenna selection, and the second one is used for hybrid beamforming application. By using this, we first select the antennas, the best antenna set that can be improve the communication performance. So instead of using all of the antennas, we can still obtain a sufficient performance by using only a small number of antennas. And we can also benefit from reduced hardware reduced efficiency. So in this case, we can use the channel matrix as input, and when we have the channel matrix as input, we can obtain the set of best antenna positions, and we can use it as a classification layer. Each class can correspond to a different set of antennas. So when we train this learning model with different channel realizations, we can obtain the best antenna set, and these antenna sets can be used to obtain the corresponding channel matrix, and it can be fed to another learning model, and at the output we can obtain the beamforming rate, FRF and the WRF. So here the FRF and the WRF are the beamforming rates at the base station and also at the users. It is also possible to use federated learning for beamforming applications. So in this case, our aim is to generate the beam towards users at the base station. So we need to train a learning model which is fed with, for example, the channel matrix, and it will at the end generate the corresponding beamforming wave so that we can steer the beams towards the users. So we first train a learning model. In case of federated learning, each user computes the parameters of the learning model. So each user has the capability to train a learning model. As you know, to train a neural network, we need a huge computation power. For example, we need to use GPUs, graphical processors. So we assume that each user has the ability to compute the learning model parameters. Once they compute these parameters, they need to send it to the base station. And at the base station, these are aggregated or averaged and sent back to the users. The main reason to do this is that the users do not have a communication between them. So we need to collect data from all of them and aggregate it at the base station and send it back to the users. So this process can be conducted iteratively, and at the end, it will finally converge to a point at which we have a trained learning model. So once we have this trained learning model, it will be located at each user. And each user can then transmit these learning model parameters to the base station. And base station can use it by feeding the channel matrix to it to obtain the learning model, to obtain the beamforming vector. It is also possible to use it for spatial path index modulation. So we still perform hybrid beamforming. However, we can apply spatial path index modulation, at which case we have a spatial phase index information which is fed to a switching network so that we can switch a certain number of RF chains to a certain number of phase shifters. By doing this, we can improve the spectral efficiency of the system, because if we don't use it, if we don't use spatial phase index modulation, the wireless communication will be performed by selecting the highest gain path. So the transmitter will use the highest gain path to communicate with the users. Instead of doing this, we will use multiple paths which have comparable gain, and we can switch it so that we can transmit to the user more information by switching and by modulating phase index. This is very similar to index modulation in frequency bands or in antennas, but this is much more efficient since it doesn't use much more complexity in terms of hardware. So it's also possible to use hybrid beamforming for the joint radar communications problem. In this case, we have a radar communication equipment which is implemented by using a hybrid beamformer. So here in this case, we implemented at a terahertz scenario, which we have thousands of antennas which are located at a subarray concept, so that each subarray can generate a single beam, and we can use a single phase shifter for each of the subarrays, and we can reduce the hardware complexity. Federated learning can also be used for channel estimation tasks. In this case, we need to collect the channel data from each of the users, and these users should also need to compute the channel matrix by using the model-based technique, and the training data are used to compute the learning models at the user level. So we only transmit the model parameters to the server, and once the model is trained, each user can use the pilot data to estimate their own channel, which is very efficient as compared to the conventional model-based technique. It is also possible to use a hybrid technique for federated and centralized learning. So federated learning is a new paradigm for model training. So most of the learning models, most of the machine learning techniques are based on centralized approach. So instead of doing this, federated learning can be used, and which can be very efficient. However, in federated learning, we have a very big assumption that the users or the clients have the capability to compute the learning model parameters, which requires huge computational power. So, for example, in case of the cell phones, we need to use a huge GPU. So we need GPUs at the mobile phones or each client. So it cannot be possible in case of a different network or network architecture. So instead of doing this, we propose to use a hybrid architecture at which we can have both centralized and federated learning. So in this case, we have a passive client which do not compute the learning model parameters because they do not have enough computational power. So instead of doing this, they perform centralized learning, which means that they transmit your data set to the server. We also have active clients. So the active clients perform federated learning, and they compute their model parameters to the parameter server. So by doing so, we still have an ongoing process of training. In case of centralized learning, we would only train a certain number of clients and their data sets. And in federated learning, we can use only a certain number of clients. In this case, all of the clients can participate in training. Deep learning can also be used for directional variable estimation, which is a very popular topic in radar applications. So in this case, the main problem as compared to the communication scenario is that in radar problem, we only have to listen to the environment. So we don't have very much information about the environment or to receive signal. So we can only have an output of the antenna, and our task is to estimate the direction of its source, for example, the source signal. So to do this, we can compute the covariance matrix of the received data at the antenna, and we can feed it and at the end we can generate the music spectra. So the music spectra corresponds to the signal corresponding to direction information. So so that we will have a peak at the spectra which corresponds to the direction of the target. So now we will talk about some future research directions, uh, which can be very helpful to the audience. So that, for example, first, federated learning for physical layer design. In physical layer design, most of the algorithms, most of the proposed approaches are based on centralized techniques instead of machine learning. So we believe that the federated learning version of these techniques will be much more present and popular in the future, in the coming years. So, for example, for physical layer design, for beamforming, channel estimation, resource allocation, or same problems with UAV networks or vehicular networks, these will be very popular because these applications are actually very applicable to the distributed scenario in case of federated learning. So for this reason, we believe that centralized approaches will be converted to federated techniques. Another one is online schemes for physical layer design because most of the papers in the literature discuss about the, for example, beamformer design, channel estimation, or resource allocation, or source detection, signal detection. These are offline techniques. So they train the neural network and they deploy it. So instead of doing this, we need online techniques which can be used to adapt the environment because the adaptation of the wireless communication environment is very essential because the data changes all the time and we need to use online techniques. So how can this be done? So we can train a learning model at first and we can update its parameters as we have new data. And label-free inference is also a very good topic because computation of label is very computationally heavy. For example, you will train a neural network, you need input. So input can be obtained. So we can see data which is in many cases if you have very big training data set. So you need to compute the label data for each of the input instances, which is computationally heavy. And this is the if in that case, for example, if you use unsupervised learning, it can be efficient. And also it is possible to use reinforcement learning techniques so that we can have a label-free inference approach. In that manner, joint reinforcement learning and federated learning approaches can be very useful and popular in the next few years because most of the papers in the literature are now in centralized learning techniques or in offline learning techniques. So online learning or it's possible to use a reinforcement learning architecture so that the neural network can adapt to the environment, and at the same time we can train the learning model in a distributed manner in case of federated learning. And the next topic can be the quantized learning model. So complexity in case of training and also in case of storage. So these learning models have huge capacity. They have a very big number of learning model parameters. For example, a conventional learning model has, for example, 2 million or 2 billion parameters. These are the learning models for wireless communication. For example, a learning model that I use, for example, for channel estimation has 2 million parameters. So we need to train them and we need to save them in the memory. So we need to have, so we can have, if we have quantized learning models, it can be useful to save and lower the size of the learning models. It is also possible to transmit them during by using some communication techniques. And finally, we unified learning models. And finally, for unified learning models, such as we can have two different techniques with two different learning models. For example, we have seen it, two different learning models for both channel estimation and higher beamforming, or for antenna selection and beamforming, or signal detection and channel estimation. So the use of multiple learning models for a certain task is very efficient way of implementing machine learning techniques in wireless communication, compared to the model-based techniques solving multiple optimization problems in the first place. So this is the end of my talk. I can ask some questions. I'll be happy to answer.
Yes, thank you for your presentation. Dear participants, do you have any question about the presentation? Okay, no question. Mr. Ahmet Elbir, thank you for the very valuable information you have provided. I wish you continued success in your career. See you in other symposium organized.
In conference?
I can't understand.
I didn't hear your question. I mean, you mean another talk in conference?
Thank you thanks for very valuable information you have provided. I said.
You're welcome.
I wish you continued success in your career.
Thank you.
Okay. No question. So I want to end the session, special session. Thank you again. Dear participants, hope to see you at next session starting at 3 o'clock p.m. I want to end the session.